Great. Thank you. Thanks to the organizers for the opportunity to speak and also for putting together such a lovely conference. I've really enjoyed all the talks so far and I'm looking forward to the rest today. So I want to tell you about some joint work with Ola Sobieska on analogs of the rational normal curves that live in weighted projective spaces. And on a few properties of them, but the one that I'm kind of most interested in that I'll talk the most about will be the Cazul property, or really the non-standard Cazul property. But I'll tell you what I mean by that in a bit. I want to start by just giving you one concrete example of the kinds of objects that we're interested in. And I'll say that this is the weighted rational curve of type 3-2. So geometrically, we'll embed P1 into a weighted projective space with weights 1, 1, 1, 2, 2. And those weights are coming from the parameters 3 and 2. You can probably kind of see how. And we'll map the point ST to the point S cubed, S squared T, ST squared, and then ST to the 5th and T to the 6th. Okay, and algebraically, I'll let S be a polynomial ring in 5 variables. And I'll name the first few x's and the last couple y0 and y1. And this corresponds to a map to a polynomial ring in 2 variables where I take x0 to s cubed and so on. So each of the variables will be mapped to one of these 5 monomials. But there's something kind of funny happening with the degrees of these monomials. It's already showing up here in the weights in our weighted projective space. And those same numbers are going to show up as the degrees of our variables. So I'll often write numbers under my variables to denote their degrees. And so I said that the objects we're interested in are these curves in weighted projective spaces, but algebraically that just means that I'm interested in some non-standard Z-graded rings. So instead of giving all of my variables degree 1, they're often going to have some other degrees like this. So I'll maybe call this map phi, and I'll let I be the kernel. And the ring that we're interested in is S mod I, or you can think of this as a subring of this polynomial ring generated by exactly the same monomials that are defining the map. So s cubed, etc., all the way up to t to the 6th. And I'll say a little bit more later about kind of where this map is coming from and what the other weighted rational curves would look like. But for now, I just want you to have at least like one example in mind of the type of non-standard graded object that I'm interested in. And so the kind of main question that I want to ask about this object is our Cazul. So that'll be the goal, but I want to tell you first a little bit about kind of how we got here. So whether you prefer to look at like the geometry side of what I've written down or the algebra side, this probably looks somewhat similar to something you've seen before, which you might think about as a rational normal curve, specifically the twisted cubic, or maybe you see this and you think like that looks kind of like a Veronese. And so here's an example in the standard graded setting that should look pretty similar, but be a lot more familiar, and that's the twisted cubic. Okay, so geometrically, now we're embedding P1 into a usual projective space, P3, and we're taking ST to the point with coordinates s cubed, s squared t, st squared, and t cubed. So now it's just all of the degree 3 monomials in S and T. And algebraically, our polynomial ring will have 4 variables. But importantly, they're now all degree 1, which is what I mean when I say that something is standard graded. And again, we'll have a map to the polynomial ring in 2 variables, where x naught gets mapped to s cubed, and so on. And I'll again call it phi, and we want to look at the kernel, or maybe rather the quotient s mod I. So this is what the twisted cubic looks like. Again, this is one example of a rational normal curve, or if you prefer, this is the third Veronese of the polynomial ring in 2 variables. And a lot is known about the twisted cubic and the rational normal curves. They're often some of the first examples of a lot of nice algebraic and homological properties. So here are a few examples of nice properties that we have. First, I is determinantal. And maybe you've seen exactly what the matrix is whose minors generate I. I is generated by the 2 by 2 minors of this matrix. So it's a really nice matrix. It's easy to write down and it's linear. And for general rational normal curves, not just the twisted cubic, there's just a very slight modification to that matrix, which you've maybe seen before. So this is one kind of nice fact about this object. The next one is that R is Cohen-Macaulay. And then another fact is that R is Kazul, or a Kazul algebra. And that's really the fact that I am most interested in. So as a little bit of like a preview of where we're headed, Ola and I kind of were interested in trying to find or understand a class of curves that could play a similar role to the rational normal curves, but in weighted projective space. And so this example and the family of weighted rational curves come from a paper of Brown and Ehrman in 2023. And we wanted to study these curves to see if maybe they had some of the same properties of the rational normal curves and whether they could play a similar role. I want to kind of like, in case the setting of non-standard gradings and multi-gradings is unfamiliar to anyone, I want to kind of warn you that there's this like overarching philosophy that we see in that area, which is that very often classical or standard graded results have analogs in the non-standard graded setting. But also, often we have to kind of make adjustments. So we might have to adjust definitions, statements, and proofs to make them work in this more general setting. So just be aware that that's kind of the overarching theme, and we should expect that the answer might not just be a simple like, yes, this object has the same properties. We might have to make some adjustments. Okay. I want to say a little bit about free resolutions and Kazul algebras in general, including in the standard graded setting, just to make sure that we all are kind of on the same page. So for the moment, I'll want R to be some Z-graded K algebra. And I'll let M be the homogeneous maximal ideal. And so a fact that many of us might already be familiar with is that any graded R module M has, I'll write just a resolution, but really what I mean is a minimal graded free resolution. And so what does that look like? We have this kind of sequence of free modules that I'll call F naught, F1, and so on, and maps in between them. The fact that it's a resolution means that there's no homology. The way that I've written it, there's no homology anywhere. If I left off the M, we would say that there's homology just at the very first spot, and specifically, the homology is M itself. The fact that it's minimal, and we saw this a bit in some talks yesterday, means that the matrices representing the maps in the resolution don't have any units. And what do these modules look like in case these aren't objects that you work with too often? They're graded free modules over R, which means that they could look, just for example, like maybe R with a twist of -1, and then some copies of R twisted by another number, maybe -3. So this is just one completely made up example, but each of our FIs is going to be some direct sum of twists of copies of R. Okay, any questions so far? Feel free to just stop me if you have questions at any point. Okay. If you haven't seen these like graded free modules or these twists before, you can just think that we are choosing the twists to make sure that all of these maps are degree preserving. Okay, so here's one example. I'll let R be a polynomial ring in two variables of degrees 1, so standard graded. And our module will be R mod the maximal ideal, which is really just the field K. So if I resolve M over R, what does that look like? It's a nice short resolution. The maps look like this, x, y, and then y, negative x. You could check that these compose to 0, and in fact that there is no homology. And so in the notation from up here, this would be F0, this is F1, and this is F2. And so I would say that this resolution has length 2, since beyond that point, everything is 0. And if you work over a polynomial ring, so if your ring R is just a polynomial ring in some number of variables, it in fact turns out that every module has a finite length resolution over R. And this is Hilbert's syzygy theorem. Which says that if R is a polynomial ring in n+1 variables, and M is a, maybe I should specify finitely generated, graded R module, then M has a minimal graded free resolution over R of length at most n. This should just be an x of n. So this is just one example, but it turns out that there was nothing special about the module I picked in terms of the fact that I got a finite length resolution. This is telling us that that would always be true. But we might not always want to work over a polynomial ring. So other rings that you could think of when you're thinking about this definition of a free resolution would be quotients of polynomial rings. And in general, if you're resolving a module over a quotient of a polynomial ring, you should expect that it very well might have infinite length. So here is one example. Where R is not a polynomial ring. And so this theorem does not apply. I'll take R to be K adjoint X mod X squared. And our module will be R mod the maximal ideal, which again is isomorphic to K. And so what does the resolution of M over this ring look like? Well, the first map will be multiplication by X because I'm quotienting by the ideal generated by X. But then what should the next map be to make sure that this remains a complex and an acyclic complex? X squared is 0 in my ring, and so if the next map is also multiplication by X, those will compose to 0, and in fact you can check that this is exactly what the map should be to make sure that I'm still building a resolution. The next twist will be -2, and that's exactly coming from the fact that X has degree 1, which I really maybe should have written down, but X has degree 1 here. And the resolution will just continue in exactly this way, and it will have infinite length. So we should really expect that this will happen when we're working over something other than just a polynomial ring itself. But there is kind of something else that we can ask for. So we can ask instead to have some kind of bounds on how bad these twists are, or on how negative the twists are, how fast they're growing. And here you can see the pattern. You can see that the twists are going to keep becoming more negative, but they're kind of doing so like as little as possible. So because we're assuming that our resolution is minimal, we're always going to have maps of at least degree 1, and that means that in order to make those maps degree preserving, we'll have to at least kind of drop in our twist by -1 each time. This resolution is kind of exactly achieving that best case scenario. It's only dropping by 1 each time. And that's coming from the fact that the maps are all linear. So that's kind of the idea, is that we're going to be working over quotients of polynomial rings. We can't expect our resolutions to have finite length, but maybe instead we can expect them to have some kind of nice bounds on what twists are showing up. And so this example is kind of the best case scenario. If you like thinking about regularity, what I'm really saying here is that the regularity over this quotient ring of the field is 0, or there's only one row in the Betty table. Okay. I want to show you another example where this doesn't happen. So now let's let R be K adjoint X mod X cubed. Doesn't look too different. It'll still be standard graded, so X will still have degree 1. And our module, again, will be the quotient of R by the maximal ideal, so just K. But let's see what the resolution looks like now. So the first map will again be multiplication by X, which means that the twist here will be -1. But because our quotient is now by X cubed and not X squared, the next map is going to have to be X squared to make sure that we're composing to 0, to make sure that we're getting a resolution. And that means that our next twist will be -3. The next map, just to give you a sense of what this looks like a little bit further out, will be multiplication by x again. So the next twist will be -4. But then we'll again, you can maybe guess, have multiplication by x squared. And it'll continue in this like alternating fashion, and it'll never stop. It'll have infinite length. But if you write out the Betti table, you'll see that it does not have finitely many rows. Or in other words, the regularity over this ring of the field of this module that we picked is infinite. So the first example kind of showed like best case scenario when we're working over a quotient of a polynomial ring, and this one is kind of showing worst case scenario in some sense. Okay, so I've written down 3 examples of resolutions, and every single time I've picked the module to be R mod the maximal ideal, which is the base field K. And there is a reason for that. So I want to say a little bit about why I keep picking sort of the same example. There's a theorem of Avramov, Eisenbud, and Pava that tells us if R is standard graded, so you should think R is a polynomial ring or a quotient of a polynomial ring where the variables all have degree 1. They tell us that there are 3 equivalent statements that all have to do with these examples we've been seeing. So the first one says that the regularity over R of K is 0, which is what we saw happen in the example on the far right. The second one says the regularity over R of K is finite. So the fact that these are equivalent is really telling me that there are only 2 things that can happen when I resolve K over a standard graded ring R. Either we get regularity 0, which is what happened in the far right example, or we actually get infinite regularity, which is what happened here. So we can't get anything in between. The third equivalent statement is kind of in a different direction, and it says that the regularity over R of M is finite for all maybe finitely generated graded modules M over R. So really why I care about this theorem is because it's telling me that if I know that the regularity of my field of this one particular module is 0, or even just that it's finite, that actually tells me a lot of information about the regularity or the resolutions of modules, of other modules over my ring. So K is in some sense giving me like the worst case behavior over all modules over this ring, is the idea here. And so we give a name to this property. But I will state this definition a little bit more generally. So the definition makes sense even if R is not standard graded. You can at least phrase it in a certain way. So we say that a Z-graded K algebra R is Kazul, or is a Kazul algebra if the resolution of K, thought of as the R module R mod the maximal ideal, has the following form. Okay, so having this form is the same as statement one, and therefore the same as all of these in the standard graded setting. But we can ask whether K has this form even if R is not standard graded. If you compare what this resolution looks like to what I wrote down just for kind of the definition of a minimal graded free resolution, the restriction that I'm making here is on the twists that show up. So I'm saying that in homological degree 1, the only twist that can show up is -1. There will be some number of copies of R twisted by -1. In homological degree 2, only the twist of -2 can show up, nothing else, and so on. It's worth mentioning, I think, that in the standard graded setting, there are several ways to phrase this, right? So I can write it down kind of concretely in terms of what the resolution looks like this. I can say that the regularity of K is 0, or instead that the Betti table for K has only one row. Also, though, in the standard graded setting, it makes sense instead to say that this is a linear free resolution. And concretely, that means that all of the entries and all of the matrices describing the maps in the resolution are linear combinations of the variables. We'll see in the non-standard graded setting that linear can mean lots of different things, and so I will try to avoid using the phrase linear in that setting just to make sure that things are clear. Any questions at this point? Okay. Okay, I'm going to leave this example up just for a moment because I just want to kind of like recap the examples we've seen in terms of this terminology. So this first example, which was just a polynomial ring, we saw was Cazul. Why? Because we resolved the field and we had exactly the right types of twists, so something matching what's happening here. The same thing happened with this second example. So here's our second example of a Cazul algebra. And our first non-example of a Cazul algebra is this guy, because the twists were not the right ones. So K join X mod X cubed, we've seen is not Cazul. So the way that we came to these three conclusions is by actually like writing down resolutions of K over these three rings. That is not always, it's not always easy. It's not always the best way to check whether something is Cazul. And so I'll tell you about just kind of one other way that it's a very, very nice way to check whether something is Cazul that doesn't involve writing down a resolution or a Betti table. So here's a nice fact about Cazulness. If I has a quadratic Grosvenor basis with respect to whatever monomial order you want, then the quotient by I is a Cazul algebra. So this, in practice, is a really nice way to check that a lot of things are Cazul algebras, is by finding a quadratic Grosvenor basis with respect to some monomial order. So, for example, the coordinate rings of rational normal curves like the twisted cubic that we saw, these are Cazul. And it's exactly because the minors of the matrix that I wrote down are not just generators for the ideal, but in fact, they're a Grosvenor basis with respect to some monomial order, and they're all quadratic. And so applying this fact kind of immediately tells me that those rings are Cazul algebras. Okay, so I think this is all I want to say about the standard graded setting. And I want to return now to what I'm really interested in, which is these weighted rational curves. I am going to write down again this kind of main example that I started with. So this is the weighted rational curve of type 3, 2. For more on like the general family and kind of where these examples came from, if you're curious, you should see a paper of Brown and Ehrman from 2023. But here's the one example that I want us to focus on. As a reminder, we mapped the point st to s cubed, s squared t, st squared, st to the fifth, and t to the sixth, which kind of looks like the monomials that show up when we define the twisted cubic, but not quite. So I'll say a little bit about kind of where they come from, or at least what the other weighted rational curves would look like. So I'll call this first parameter D and this one E. These can be any positive integers. If you look at the paper of Brown and Ehrman, you'll also see that there's this piece of data, a divisor that we have to pick. And the weighted rational curves that I'm talking about that me and Ola looked at are specifically for the choice of divisor just being a single point, the point 0, 1. Okay, so where are these maps actually coming from once we pick capital D and then these parameters D and E? The first several, so these first three, are the degree D monomials, but not all of them. It's only the ones that vanish at that chosen point, capital D. And then where are these last couple coming from? These are kind of, I'll be a little bit vague. They're kind of the rest of the degree D times E, so in this case, 6 monomials. What do I mean by the rest of? I mean that these three monomials, the first three, kind of generate a bunch of the degree D times E monomials. The only ones that they don't generate are these two. And so those are the two that we have to include. Again, if you're curious about where this construction came from, you should see the paper of Brown and Ehrman. The terminology here is log complete series, if you are curious about the details. Okay, and algebraically, again, we had a polynomial ring in 5 variables. Mapping to a polynomial ring in S and T, where the x's and the y's mapped to exactly these same 5 monomials that can be described kind of in this way. And as with the twisted cubic, we're really interested in the kernel of this map and in the quotient. And again, the overarching question was, do these objects, these weighted rational curves and their coordinate rings, have some of the same nice properties that we see for the rational normal curves? I'll briefly mention that maybe one of the first properties that you might think of that I didn't mention before is that the rational normal curves are normal, and these ones are not. And you could very quickly check, like you could find a specific element that shows you that these rings are not normal. But that's also kind of too much to hope for, I think, because weighted projective spaces in general are not smooth. And so these curves are somehow kind of inheriting the non-smoothness in some way. But it is reasonable to ask whether these rings have some of the other properties that we saw for the twisted cubic. So, yeah.
You're saying you're only considering 2 distinct weights, like you're
Yes.
gonna have D1s and
Yes.
But
And EEs. It's kind of weird. Yeah.
okay.
Yeah, so when like what we have called weighted rational curves will always have the form that you just said. So they're living inside of a certain type of weighted projective space.
You have no label.
Wait, could D be zero?
Yeah. Well, I guess no, that's nonsense.
Yeah.
Then you get the same. Okay, I take
Could
that back.
could D be like one, maybe?
If you have all the same, but you can divide by your back. You won't, I think you want something.
I mean, if D was zero, then D times E would be zero too, which seems bad.
I was just wondering if you could drop the rate of one, because that's when things get
Yeah, that's a good question.
interesting.
But I think, like you said, if you really dropped the weight of one and everything else was the same weight, then
Yeah, that's
okay.
interesting.
Okay.
That's just, you can, by well-formedness, you can just get it back down.
Right.
Whatever you do.
Right.
Well, whatever.
Yeah.
Okay, so we are assuming some number of ones and E's.
Absolutely. Yeah. 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 So I mean, I will say that if you look at the paper of Brown and Ehrman, there's certainly like the objects that they introduce is a wider class than this class of curves. We restricted to something like very concrete and really in the hopes that we could somehow mirror the theory of rational normal curves, right? We want something really concrete that we can actually get our hands on, write down the equations for, and understand as well as possible. Okay, so here are maybe the first couple of facts about these objects. So the first is that the ideal, again, is determinantal, which is maybe the first thing we would hope for, given what we saw with the twisted cubic. And I can tell you again what the matrix is. So I will be generated by 2 by 2 minors of a certain 2 by something matrix. Given what we saw with the rational normal curves, what you might kind of first guess is that the matrix could look something like this. So x naught, x1, x2, y naught, x1, x2, y naught, y1. And this is like literally what I would expect for a rational normal curve. But the issue here is that if we kind of focus in on this column with the x2 and the y naught, it's giving me a bunch of minors that are not homogeneous. And that's because, and maybe I should write this down again, because it really is important. The x's have degree 1 and the y's have degree 2. Okay, so again, like first thing that you might think of to try to fix this, and it might seem kind of silly, is just to raise that x2 to the power of 2. You could check that all of these minors are in the kernel, that they all do really map to 0 under phi. And in fact, this is exactly the right description for the generators of I. So this kind of silly little fix is enough to tell me what the generators are. I'll say a little bit about the proof. So in the standard graded setting, one way that you can prove that I is generated by the minors of the matrix that I wrote down is by, you can easily get one inclusion. And then you can do a Hilbert series comparison, or even just like a Hilbert function comparison. So you can compute the Hilbert function of the quotient by your determinantal ideal and the quotient by the kernel, and you can show that they're the same. And so Ola and I, we decided we would try to follow a similar type of argument, and you can make a similar type of argument, but a few things become quite a bit more difficult. So computing each of the 2 Hilbert series becomes a bit more difficult exactly because we have these like multiple different degrees showing up in our variables. But then comparing them and showing that they're equal is really what becomes quite challenging. I won't write the Hilbert series down because they're a total mess, but it's not at all obvious when you look at them that they are giving you the same expression. So this is an example of how proofs can change as we move from the standard graded setting to the non-standard graded setting. We also see that the statement has changed a little bit, although not too much. Another fact about these objects is that R is, as we also might hope, Cohen-Macaulay. But I said that the thing that I was most interested in was the Kazul property. And the reason that I'm most interested in it is kind of because something breaks a little bit, or it at least at first glance looks like it. So what happens if we try to resolve the field over our ring? Well, the first map should be given by our variables. And unfortunately, that immediately introduces an issue because it means that my twists would be -1, 3 copies of r twisted by -1, but also 2 copies of r twisted by -2. And it really doesn't even matter what happens beyond that point, because if you think back to the definition that I gave for a Kazul algebra, the fact that this -2 is showing up here at all tells me immediately that this object does not satisfy the Kazul property, at least as stated. But this is something that happens a lot in the non-standard graded setting and in the multi-graded setting. As I said at the start of the talk, we kind of expect that we might have to make adjustments to definitions and to statements and to proofs. And so maybe really this is not such a bad thing. Maybe it just means that we're not asking the right question just yet. And so I want to tell you about a definition for a related property that was introduced by Herzog, Reiner, and Welker. So they say that the Z-graded K-algebra R is, I will say, non-standard Kazul, just to distinguish, if the associated graded of R is Kazul, where I mean Kazul in the usual sense. Okay, so I want to show you a couple of small examples to give you a sense of what happens when we take the associated graded. So maybe the smallest example I would want to think about would be just a polynomial ring, where maybe the degrees are 1 and 3. If I take the associated graded of this ring, maybe I'll remind you what the definition is. So the definition of the associated graded is a direct sum R mod m plus m mod m squared plus m squared mod m cubed, and so on, where importantly, everything in this piece will have degree 0 by definition. Everything in this piece will have degree 1, and so on. And so if you kind of break it up into pieces and see what happens, you'll see that the associated graded here is just the exact same polynomial ring, but now both of the degrees will kind of by definition of the associated graded object have degree 1. And this is, we saw, Kazul in the usual sense. So that tells me that R is non-standard Kazul. Okay, perhaps a slightly more interesting example would be something involving some kind of quotient. So again, I'll give the variables degrees 1 and 3. And I'll quotient maybe by something like y squared minus x cubed y minus x to the 6th. And you can check that that's a homogeneous ideal with respect to my non-standard grading. And if I take the associated graded, it works out to be a quotient of the same polynomial ring, but now standard graded. And the other thing that changes is what we're quotienting by, and in this case, it turns out that the quotient is by just y squared. And this isn't exactly an example that we saw, but you could probably resolve k over this ring and see what happens. This is also Cazul. Or I suppose you could also observe that the ideal has a quadratic Grosvenor basis. And so this ring R, we would also say, is non-standard Cazul. So maybe the right question to ask about this main example and about the weighted rational curves is not whether R is Cazul in the usual sense, it's absolutely not, but instead whether it's non-standard Cazul. So is R non-standard Cazul where this is the coordinate ring of either this particular example or maybe one of these weighted rational curves in general. Okay, so I'll focus mostly on this concrete example, and I want to tell you what the associated graded ends up looking like in this case. You might already be able to guess from these examples that we've seen that it'll be some kind of quotient of a polynomial ring in the same variables, but all with degree 1, which is exactly right. And your first guess of what we quotient by, if you were to make one, would also probably be right. So we end up quotienting by the ideal of 2 by 2 minors of another very nice matrix. This time it's x naught x1, 0, y naught, x1, x2, y naught, y1. So that one kind of funny entry that we had to square is replaced with a 0, and the 2 by 2 minors of that matrix exactly give us the ideal that defines the associated graded. So now we're in a standard graded setting, which means that I can say that these minors are quadratic and there's no kind of question about what I mean. And in fact, these minors are in particular, quadratic Grosvenor basis with respect to some monomial order. And so R is non-standard Cazul. And you can probably also guess what would happen if we picked a different D and E, how this matrix would change. It would be very similar, a very similar story, just with kind of more columns as those numbers grow. Okay, and so everything that I've stated so far was kind of about this one particular example, but it turns out that all of these observations are true in general. So if R is the coordinate ring of a weighted rational curve, then all of these facts hold. So I is determinantal, and we could write down the matrix. It would be very similar to the one over there. R is Cohen-Macaulay. And then R has this non-standard Cazul property.
It's always given by that same 2 by 2 minor where you took the previous one and just dropped the function transition.
Absolutely, yeah. I will also mention, so I kind of focused on this idea of a proof that uses a quadratic Grosvenor basis. But I will also say we relied a lot on this paper of Herzog, Reiner, and Welker, and they have a very nice criteria for non-standard causalness for certain semigroup algebras that in fact applies in our case. So we can compute the Hilbert series of our associated graded and prove that R is of minimal multiplicity, and then they have a nice criteria that also tells us that our ring is non-standard causal.
Say R is of minimal multiplicity.
Yeah.
What is multiplicity? Is that it?
I don't think that I could tell you exactly the definition right now, but I think that they define the multiplicity of R to be the multiplicity of the associated graded. And then it's something like yeah, so you might not find that very satisfying, but I think you write the Hilbert series like in its reduced form, and you evaluate the numerator at 1. Yeah, but for the associated graded. Yeah. Okay, so I'll just take a minute to say a little bit about some possible future directions. And the idea that I want to leave you with is just that this non-standard causal property, I think there's a lot that remains unknown about it. And so there are a lot of interesting questions that remain open about, what kinds of things have this property, and also what are some ways that we could maybe prove that things have this property other than the ones that I touched on here. So concretely, there are higher genus curves introduced by Brown and Ehrman, and it would be very natural to ask whether their coordinate rings are also non-standard causal. Bojana Martinova and I have been very interested in Veronese's of non-standard graded polynomial rings, and we're interested in the question of when those Veroneses are non-standard causal. And then I would also be interested in, having other ways to prove non-standard causalness, ideally ones that don't rely on computing the associated graded and specifically computing a quadratic Grobner basis for its defining ideal. So is there a criteria for non-standard causalness that says something just about a Grobner basis that's maybe quadratic in some sense in your original ring? Or is there some kind of like analog of the theorem that we saw of Avramov, Eisenbud, and Pava for non-standard causalness? Certainly some kind of adjustment would have to be made to the notion of regularity. So those are some of the questions that I think it would be interesting to think more about. So I think I will stop there, but I'm happy to take questions.
Setting, if we have a ring of is it always causal? Is it not really causal?
That's a great question that I don't know the answer to. The theorem that we used from Herzog, Reiner, and Welker was specifically about certain like semigroup algebras. So I don't know in general. That's a great question.
Also, to check something is causal, you just need quadratic Grobner basis with respect to some order, right? Or
Yeah.
is it like equivalent to having quadratic basis in any order with respect to any order?
This is a really great question. So I probably should have said that having a quadratic Grobner basis is a sufficient but not necessary condition for causalness. And so there are examples of causal algebras that do not have a quadratic Grobner basis in any order. But yes, if you find a quadratic Grobner basis with respect to any order, then you have causalness. Yeah.
So it seems like when you're taking like something graded material from non-standard graded ring, you find a term which like tries to balance out that it's homogeneous. It's like being homogeneous just vanish. Like is it a coincidence?
Are you talking about the fact that like here, these couple of and there, yeah. So really what's happening is we're taking, if we look at this polynomial, for example, we're taking the term that is standard graded lowest degree, or in other words, that lies in, I guess, the lowest power of m, or we're sending to 0 things that lie in a higher power of m, is what's happening there. Yeah.
No, I think
Yeah, so one thing that is known, and this comes from a paper of Herzog and Iyengar, is they actually define non-standard Kazoo modules, but it's very similar. It just says that a module is non-standard Kazoo if its associated graded has a linear resolution over the associated graded of the ring. And so non-standard Kazoo algebra could be phrased in terms of that definition, where you take the module to be K. So I said that their definition asks for the associated graded to have a linear resolution, but they actually tell us that there are three equivalent notions. So one is the associated graded has a linear resolution. One is the linear part of the resolution over the original ring is a cyclic. And the other is that the linear part specifically resolves what you want it to. So it resolves the associated graded. Yeah, so let me maybe phrase that slightly better. A better answer, I think, to Lauren's question would be what non-standard Kazoo-ness tells us about the resolution over the original ring is that if I take its linear part, I get something that is still a resolution. And specifically what I get is the resolution over the associated graded. Yes, yeah. Oh, I should definitely know the answer to that. But I don't. In general, the associated grades get worse in some sense. Like this ideal isn't prime. I certainly should know the answer to that question, but off the top of my head, I do not remember.
Let's think of it over.